So why don't you realize over here, when you read the question, so I'll explain to you in real time how you go about showing that A is equal to this. So you understand all they want you to do is writing down the equation proving that A, which is the surface area, the internal surface area, comes out to this particular sequence. So the best way to go about doing this is, even if you didn't know the numbers, you'd realize that if you want to prove that A is definitely equal to this, if you want to prove the internal surface area is given by this formula, remember what we do? We don't focus on the numbers just yet. We just realize what even makes up, do we even know what the surface area is? What would make up the internal surface area? And you realize if they're telling you it's modeled as a closed cylinder, they're basically saying the internal surface area, in this case, is the internal surface area of a cylinder. And common sense tells us what? If we have a cylinder, the internal surface area, do we know that it's just going to be the area on the inside? What makes up the area on the inside? See these two circles? You see what we're getting at? The logic over here that has to happen first. We have to realize what even makes up the internal surface area of the shape before we even write down the numbers that represent the internal surface area, which is over here, which is what we're trying to prove. So we realize there's two circles. There's the top one and the bottom one that make up the internal surface area, and there's also the side what? The side panels. Unravel that, yes. The inside of that cylinder. And do we realize, can you visualize that when you unwrap the inside of a cylinder, you actually have a rectangle? Confirm you understand that it's a rectangle when you unwrap the cylinder. And if you have a rectangle, if you want to find the area of the rectangle, because you're talking about the internal surface area, right? You need the area of that rectangle. The area of the rectangle comes from what? It's not any different from any rectangle in general. It's going to be the length and the height, which is the height over here, and the length of that rectangle, which is the same thing as what? The circumference of one of the circles. The point is, you realize these are the three shapes that make up the internal surface area, and then you go about doing it that way, which is, well, you know what represents the two surface areas of the circles? 2 pi r squared. See how that explains our first line of working over here? A is equal to the 2 pi r squared for the circle, and the 2 pi r, which represents the circumference of one of the circles, multiplied with h, which overall gives the what? Rectangle area. The rectangle you get when you unwrap the cylinder. Do you see my point? If you were confused about this question, obviously when you do this question, the best way to go about it is you're supposed to be able to write this whole thing straight away. But if you don't get it straight away and you need to think about it, you think about it this way. You don't think too much about the numbers. You focus on, do I even know what the internal surface area of a cylinder is? Do I even realize that's all they're asking me to do, right? It starts off by finding whatever makes up the internal surface area of a cylinder, which is two circles and the rectangle you unwrap from that cylinder. Here. And once you have this first line of working, you compare this. I'm just explaining to you in real time the logic here. As in, you compare it with this. As the objective is just to turn this into this now. What do you see as differences? 2 pi r squared, is that already what it needs to be? You recognize, oh, okay, the final thing doesn't have the letter h. We have the letter h in here. So therefore, what? All we really need to focus on is how do we replace h with something involving the letter r, which is an equation involving h and r, which is what's the relationship between h and r? And then now you go back to the rest of the question, right? Oh, they're telling us the volume of the flask is 1,000, which means what? Is the volume going to involve the height? Of course. Because we're talking about the volume of the flask, which is the volume of the cylinder now, isn't it? See what we're doing there? We'd realize, oh, the volume of the flask is 1,000. Same thing as saying V is equal to 1,000. And what's V? V is for the cylinder. So what's the cylinder formula? Cylinder volume is always pi r squared, h. Pi r squared, h equals to 1,000. Do we see, just from this one statement alone, just from this one equation, we're able to rearrange to get that A is h is equal to something we want, isn't it? We're able to rearrange for h with something involving the letter r. So we can replace the h over here with this expression, h is equal to this, and that's what we did over here. And the rest you can tell exactly how this becomes 2,000 over r. Because check it out. 2,000 over r, isn't this the 2 going to be multiplied with 1,000? You know the rule when you're multiplying a number by a fraction? You just realize, oh, it's just going to be horizontal multiplication over here. 2,000 pi r over pi r squared. Pi's cancel out, don't they? The r cancels out with the bottom one to leave only one on there on the bottom. 2 times 1,000, which is 2,000, 2,000 over r. So 2 pi r squared plus 2,000 over r, just like that. Proven. Part 2. Prove that the stationary value is most efficient. First off, if they want you to ask to find the stationary value, why don't you go ahead and find the stationary value? You should know by now it's just going to be differentiate this with respect to r, dA dr, and you differentiate that. Realize that to differentiate this part, you have to write it into a familiar format, which is 2,000. R to the power of -1 first. You know exactly why. Because there's an acceptable differentiation format that must happen first before we differentiate, and then of course differentiating that gives you -1 times 2,000, which is minus 2,000. R to the power of -1 minus 1, which is r to the power of -2, making this equal to 0, and then making this equal to 0. And you can see where this is going now. There's a lot of ways you can go about solving this. You could solve this by making this also a fraction. You might be tempted to do that, but you realize, isn't it much easier if you just move this to the other side? You sort of predict beforehand think a few steps ahead, right? It's not difficult to do that. See how moving this to the other side? You sort of predict by moving this to the other sides, you can create a cross multiplication scenario, which definitely helps to rearrange for the r itself. Getting r by itself, right? The whole point of algebra over here is to get r by itself. Because you know if you have r by itself, you've definitely found what the missing radius is. And they're asking you, what's the radius value that gives you a stationary value? What's the radius value that gives you dA dr equals to 0? Because that's the definition of stationary value, isn't it? The gradient function equals to 0. And the last part over here, if you were to verify that it's most efficient when it takes this value, think about the definition over here. If we're not worried about the math just yet, do we even know what verifying it's most efficient even means? It's about realizing at the beginning of the question, they tell you what? It's most efficient when the total internal surface area is a minimum. It's the same thing as saying the minimum value of A. When A is a minimum, it's most efficient. So if we found out this is where it's going to be a minimum, how do we prove it's going to be a minimum? It's just going to be what? Substituting this into the double derivative to prove that the double derivative is positive or negative. Positive. Which is what we've written over here. This is just the instruction for the double derivative, which comes from differentiating this, right? This becomes 4 pi, no problem. You see exactly that comes 4 pi. This is going to be negative 2 times minus 2,000, which is plus 4,000, times r to the power negative 3, which is the same thing as dividing the whole thing by r to the power 3 on the bottom. We replaced r with 5.42 because we want to substitute the 5.42 for the radius over here. Because we're trying to find what the double derivative is when r is equal to 5.42. And then without further ado, this is where we get proof that it's positive. And then last step, right? Just state your conclusion. When the radius is 5.42, it's the most efficient. Because we've proven it over here. And we found the radius that gives you a stationary value.